Neuromuscular junction means a connection between a neuron and a muscle. So if you look at it here, you see that this is the end of a neuron, and this is the plasma membrane of the neuron. This is called the presynaptic membrane. Okay, and that area contains also these vesicles. The vesicles contains acetylcholine. This is acetylcholine. Okay, contains acetylcholine, which is a neurotransmitter. It's a chemical. Then you have this. This is a plasma membrane of the muscle. This is the T-tubule of the plasma membrane. This is called also post-synaptic membrane. And the area in between this area, this is called synaptic cleft. Synaptic cleft, that is a space between presynaptic and postsynaptic membrane. You also have these receptors that are responsive to the acetylcholine. So I will show you what will happen to those receptors. And you have some enzymes here. These are called acetylcholine esterase that breaks down acetylcholine. So the motor end plate is the area that the nerve connects to a muscle fiber, and that is the area that the muscle fiber can be activated. So what happens here, an action potential arrives. An action potential, in case if you forgot from Bio 1, is that changing in the membrane potential of the neuron, and that will cause movement of sodium inside the cell. The inside the cell become more positive. So action potential comes here. Once it gets to the presynaptic membrane, then calcium enters the cell, which is not shown here, and that calcium will cause fusion of these vesicles into the presynaptic membrane. Once they fuse here, then the neurotransmitters, which are acetylcholine, they are released in the synaptic cleft here. Now they go on attached in these receptors, and these are the sodium channels. So once they are attached to these ones, the sodium channels open up and the sodium enters the cell. Once the sodium enters the cell of the skeletal muscle fiber, inside the cell become positive, and that is a change in the membrane potential. So that will cause, initially graded potential and then an action potential. So here you will have the T-tubules are also activated here. Then you have these acetylcholines are attached to acetylcholine esterase, and that acetylcholine esterase breaks it down, break down the acetylcholine, and it will be recycled back. So when the next time there's a need for it, then it can be used right away. So excitation, contraction, coupling, what does it mean? It means that the nerve has to be excited or stimulated, and that stimulation comes to the muscle and cause contraction of the muscle. So these two has to happen back to back, and if that does not happen, then no muscle activity will happen. So here is the neural activity. This is a neuron, and this is the branches of a muscle fiber that is attached to the sarcolemma of the muscle fiber. So then this is the ending. They have these vesicles, and this is the end of this neuron. So this is called axon, and they have these vesicles there. This is contain acetylcholine. So when there is a stimulation there, the acetylcholine is released, and then activating the plasma membrane, and that will go to the T-tubule. So now the T-tubule is located close to the sarcoplasmic reticulum, and if you remember, the sarcoplasmic reticulum is covering or surrounding the myofibrils. So here the sarcoplasmic reticulum contains calcium, and that calcium is released, and that will cause muscle contraction. So up to here, when the neurotransmitters are released from an upcoming action potential of the nerve, and then the plasma membrane of the skeletal muscle is activated. That's the excitation part, and then once the calcium is released, and that will cause movement of the thin filament over the thick filament, that is the contraction part. So if this excitation is not there, this contraction will not take place. Okay, so what we see here is that you can see the F strand, F actin strand, and these are the G acting molecules that contains the active site. Normally the active site is covered by tropomyosin, and you also have troponin here. So there is no calcium there, and the active site is covered by tropomyosin, so there is nothing happening. No connection between myosin and actin will happen here. Once the calcium enters from sarcoplasmic reticulum, as we saw before, so now the calcium attaches to troponin, and troponin moves tropomyosin. So once the tropomyosin is moved, then what will happen here? The active site of actin is exposed. You can also see here a nebulin that are connecting these G-acting molecules. Then what will happen that the head of the myosin comes and attaches to active site of actin, and this action is called cross bridge. So cross bridges when the head of the myosin comes and attaches to the active site of actin. If you look at it from sideways, so you want to know what's going on in the contraction cycle, here you have the F-acting strand, and these are G-acting molecules. This is the nebulin, and this is the tropomyosin that covers the active site of actin, and there is a tropomyosin that is keeping the troponin that's keeping the tropomyosin there. So when there is no calcium, nothing is going on. Okay. Also, you see that you have the myosin, and you have the head of the myosin that contains an energy molecule, which is ADP plus phosphate. So once the calcium enters the area, what will happen that the calcium again attaches to the troponin. Troponin moves tropomyosin, and now the active site of actin is exposed. The active site of actin is exposed here. Once the active site of actin is exposed, and the myosin head also has energy that goes and attaches here. So that will cause a cross bridge. Okay, so that attachment of the head of the myosin to the active site of actin. Then the head of the myosin moves the actin toward the midline. Okay, it moves it toward the head midline, and that will cause a release of ADP and phosphate. So now this is the sliding filament theory that I talked about it before. This is what's happening. So the H band is decreasing, and the thin filament is sliding over the thick filament. Then what happens that ATP, another ATP molecule comes here, attaches to the myosin head. So this attachment will cause detachment of the myosin head from the active site of actin. Okay, detachment. Now the ATP hydrolyzes again to ADP and phosphate. That will result in the movement of the myosin head back to the same way it was. So when it goes back to that and the calcium is still there, it means the active site of actin is still open. Then the myosin head goes back and attaches to the active site of actin again and moves actin again toward the midline. So this happens many times. So when it moves it toward the midline, that is called power stroke, moving it toward the midline.